Hello everyone. Today I'm going to speak about dispersion diagram. One of the main application of metamaterial is suppression of surface wave. To analyze whether surface waves are propagating or if it is suppressed, we usually use dispersion diagram. So in this video, I'm going to explain what is dispersion diagram, how it is made, and what type of information we can get from that. So first of all, let's see what an electromagnetic band gap structure is. So these are usually periodic array of structures over a grounded plane, and usually these patterns will be connected to the ground plane through wires. So these are two examples of EBGs. So the main application of EBG is they will prevent the propagation of electromagnetic waves in a specified band of frequency for all angle of incidence and for all polarization. So to analyze the surface waves, we usually consider the unit cell. So here in this structure, the unit cell is hexagonal in shape, and in this case, the unit cell is a square shape. So why we are using the unit cell for the analysis is it is based on the Bloch's theorem. Bloch's theorem states that waves in a periodic structure take on the same symmetry and periodicity as in the periodic elements. So what does it means that in a periodic structure, if we will get the entire structure if we repeat the unit cell. Similarly, if we want to analyze the surface waves in the entire structure, we have to only consider the unit cell and we have to analyze it because the surface wave property on the entire structure will be the same as what we are going to observe on a single unit cell. Okay, let's see what a dispersion diagram is. So this is how a dispersion diagram will look like. And in this case, we can see that the frequency uh, in gigahertz is plotted along y-axis and wave number is plotted along x-axis. Sometimes we plot frequency in radian per second along y-axis and wave number along x-axis. So dispersion diagram is a omega beta plot representing all the type of waves propagating in that metamaterial or whatever structure we are considering. So in case of when the we are considering the wave propagation in vacuum, we know that the relation between omega and beta become will be equal to 1 by mu 0 epsilon. This will be like speed of light. That means that in vacuum the wave is propagating without any dispersion or anything. So when we plot that line, it will be a straight line and we will be calling it as light line because this represents a plane wave propagating through the vacuum without any dispersion. So the wave which is dispersing will be having the velocity less than the light line. So all the surface wave will be appearing below or on the right hand side of this light line. That is why we are seeing these surface waves on the right side of the light line. So what other information we can get from this dispersion plot? Here we can see that we have plotted the surface waves like first mode surface wave, second mode surface wave, etc. So here in this range that is from the frequency 3.5 gigahertz to 6 gigahertz, we can see that there is no surface wave propagation. This means that from 3.5 to 6 gigahertz, this electromagnetic band gap structure is suppressing the surface waves. And another information that we can get from this plot is phase velocity and group velocity information. So the phase velocity is the ratio of omega by beta and the group velocity is d omega by d beta. So in case of the plane wave, that is if we consider the light line or the wave propagation in vacuum, we know that the phase velocity and group velocity will be the same. But when we consider these surface waves, we can see that the omega by beta and d omega by d beta will be different. That means phase velocity and group velocity of the surface wave will be different. And here also that means that it is dispersive in nature. That is, surface waves are dispersive in nature. And one more information that we can obtain, that we can see in this picture, is on the x-axis it is represented gamma x m. So this is known as the irreducible Brillouin zone, and in upcoming slides I will explain what it is. Let's see how the x-axis on the dispersion diagram, that is gamma, x and m, are formed. For that, I'm going to consider a periodic structure like this. This is known as the direct lattice because it is a periodic function of physical space. Whatever the structure we are having is, we are calling it as the direct lattice. For the simplification of analysis purpose, I am going to take a unit cell from the direct lattice. So this is the unit cell from the direct lattice. Here we can represent the unit cell as T1 equal to AX cap and T2 equal to AY cap. So nothing complex here, where A is represented by the periodicity in x-axis and A is the periodicity in y-axis. These are same as we are considering the square lattice. So next important step is, as we are considering the dispersion diagram, in dispersion diagram we are plotting frequency and wave number. So we have to convert this physical space into a spatial frequency domain. For that, what we have to do is we have to take the FFT. So when we do that, we call that lattice as reciprocal lattice. So the reciprocal lattice is the dual of physical space represented in mathematical space or spatial frequency. So nothing complex, it is just the FFT of the direct lattice. And here is the reciprocal lattice. Here we can see that T1 is equal to 2 pi by AX cap and T2 equal to 2 pi by AY cap. Here we can see that the dimension of the reciprocal lattice is getting increased. So next step is we have to consider the unit cell from the reciprocal lattice. So as I have considered only a single cell from the direct lattice, this cell will become the unit cell. So the unit cell of the reciprocal lattice is known as Brillouin zone. So here I'm just going to represent the dimension of these Brillouin zone, because here the total dimension is 2 pi a. So here it will be divided into the symmetrical shape. So the minimum x dimension is minus pi by a to pi by a, and the y dimension will be minus pi by a to pi by a. Next step is we have to take the irreducible Brillouin zone. That means we have to take the smallest volume from this Brillouin zone, which can entirely represents the total structure. So this is the irreducible Brillouin zone for this square lattice, and uh, its structure is represented by gamma, x and m. So in the next slide, I am going to explain how we are getting this irreducible Brillouin zone from the Brillouin zone, and why we are using this gamma and x and m in our dispersion diagram. Okay, so I'm going to consider the Brillouin zone from the previous slide. So here it is the dimension and this is the Brillouin zone. So our aim is to produce the irreducible Brillouin zone from this structure. So first what we are going to do is we will be checking whether it has up and down symmetry. As it is a square lattice, we can see that it has up-down symmetry. So uh, for the simplification, we have to consider only this up portion. We can avoid the down portion. So here we will be considering only the up portion. So in next step, what we are going to do is we will be checking whether it has left and right hand symmetry on the upper portion. So as it has left and right symmetry, we will be considering only a one part that is represented on the next picture. So we can avoid this much portion also. Next is, so now we have this much portion. So in this portion, what we are going to do is we are going to check whether if we cut this domain into half, whether it has rotational symmetry. Because we know that when we cut it half, if we expand that, it can cover the entire structure. We can say that it has rotational geometry and we have to consider only a portion of that. So now we get this dimension, only this much structure we have to consider, and if we repeat this structure entirely, we can produce the entire Brillouin zones. And we are going to check again whether we can reduce it further. But we can see that if we divide it again, it will means it will remove the symmetry of the structure. So it is not possible to reduce the symmetry of this structure further. So we call it as this is the irreducible Brillouin zone, and we will be considering this much structure for our analysis. So that is represented here. So this is the irreducible Brillouin zone having the dimension like minus pi by a to pi by a, and our area used for consideration is this much. And let's see how this naming like gamma, x and m are made. For that, we have to consider the Brillouin zone of a simple cube. In case of a simple cube, this is the Brillouin zone, and here we can see that this gamma is represented on the mid of the cube. So similarly, we can name the mid of the cube as gamma, and x is represented on the center of the face, and here we are going to name x on the center of here, and m is named on the edge. That is why we are naming m here. That is how this naming is made. Based on the symbol cubic Brillouin zone, we got gamma, x and m on our irreducible Brillouin zone. So these values are represented on the x-axis. In next slide, we can see more about it. Okay, so this is our dispersion diagram, and along y-axis we have the frequency, and along x-axis we have gamma, x and m and gamma. That is gamma to x here, x to m, x to m here, m to gamma here, m to gamma here. So the complete rotation of this irreducible Brillouin zone is represented along the x-axis in dispersion diagram. So what we are means expanding here is these phase, because we can see that this phase is whatever is changing along the x y axis. So for gamma we can see that the phase along x and phase along y axis is 0 0, and in case of x the phase along x axis is pi, and phase along y-axis is 0, and here it will be phase along x-axis is pi and phase along y-axis is pi. So why we are not considering this pi by a is that because as we are considering the entire structure, we have to consider only the phase variation pi. So these value changes is represented along these x-axis. So during these simulations, we have to consider like if you are going to do any CST or HFSS simulations, if we want to plot these values along x-axis, we have to vary phase x and phase y dimension like this. Then we will be getting the dispersion diagram. So in upcoming video, I'll be explaining how the dispersion diagram can be plotted using the CST. Stay tuned for that. Thank you so much for listening. If you find this video useful, please like, comment, share and subscribe. Thank you.